Hi everyone, thank you Professor, good afternoon. My name is Christian Silva. I'm a development engineer from INEGI. We are from Porto, Portugal, and I'm here to present our research entitled Crashworthiness Evaluation of a Railway Coach. It's a numerical study towards certification and failure mitigation. Okay, so I'll just start with a quick context of the project. This is a national project called Trans Solutions Portugal, which aims to develop and manufacture rolling stock in Portugal. Right now, we don't have Portuguese production. So this project aims to do that, and we are doing the manufacturing and to this stage the design of a new train, which will consist of 3 carriages. My team at INEGI is responsible for the calculation part for homologation. So for that, we are using, of course, European regulations, and we have to look at verification of static requirements and also of crashworthiness requirements of these regulations. So this research is focused on the verification of the crashworthiness according to that regulation. So in terms of objectives, we aim to evaluate crashworthiness of a railway structure under a head-on collision. For that, we used finite element method and simulations, explicit simulations, to try and identify possible failure regions. We did that, and we were able to identify a series of structural weaknesses that, of course, could compromise survival space and put passengers at risk. And after that, we recommended some improvements. And in this research, we also compared the baseline model and the improved design in terms of failure, and also with the perspective of the regulation. And overall, the objective of our work is to support safer railway design by anticipating and preventing failure risks. So brief theoretical background of the European regulation, it's European Regulation 15227, and it defines all the crashworthiness requirements for railway vehicle structures. It defines the collision scenarios, a series of them that we have to simulate in order for the structure to be approved. And also it defines a series of safety design requirements in terms of overriding, so the contact with tracks, and also survival space and acceleration levels that we need to be within a certain values. So moving to the methodology of what we did. Of course, a big chunk of our work was to develop the finite element model, and we chose an approach quite specific, and we decided to model in a huge detail of the structure. And we're also talking about an intermediate coach of around 26 meters. So you can imagine, as I have it there, we have an element model of around 16 million elements. And we also went to the detail of even modeling the connection between components, that this train it's supposed to be of spot modes. So we even modeled that connection with spring elements and beam elements. So it's quite a refined and detailed model. In terms of material for this crash analysis, we used the Johnson-Cook material model to formulate the elastoplastic and the failure of the material. And of course, we had to model contact. We did that in a general contact to have all the structure coming into contact with itself. Because of course we don't know which components would come into contact, so we have to do a general one. And then sliding the friction with rigid bodies that I'll show in the next slide. This is an image that shows the collision scenario. I have to say this is not one of the normative scenarios. It's a simplified scenario that's easier to simulate. And it consists of a head-on collision with a rigid wall that is stationary. Basically, we have our structure with an initial velocity of 18 kilometers per hour, which is around the velocity of the regulation, and it's colliding with this rigid wall. We also modeled a rigid floor with the intention to simulate the interface with the buoys, which is the suspension of our vehicle. And also, we simulated the buffers, which are those two components in the front, which are the first component that comes into contact in case of a collision, and they deform with this graph, and of course, they also absorb energy. So it was important to also model. And we did that with simple spring elements with this characteristic curve. So now to show some results of what we found. Here's a nice video of the original vehicle structure. We can already see the propagation wave, and of course, visually, we can already see a critical region, have a detailed image of the final step of the simulation. Of course, we can clearly see that we have a critical region around the transition of the chassis and the floor, with high deformation and collapse of the members. Here I have some other details of critical failure regions that would indicate as critical, and there would be the floor cross members, also around the angle area and the doors and first window. The issue is specifically this. When we have this kind of deformation in the area of doors and windows, of course, we are coming into putting eventually passengers at entry. So because of that, and also with other static results that we had to simulate, the structure went through a lot of changes. Here I just show as a comparison of the structures. This is the chassis comparison. I show this because it's around that failure region. And because it was the biggest change, we did, but the company that is supposed to manufacture this made a bigger transition region to try and mitigate that effect in between the chassis and the floor, which is very rigid, and then it goes to the floor of the train, which is much more flexible. And we had those issues that we simulated, or that we found through simulation. So here we have a comparison of, the first video and then the modified structure. We can already see a different dynamic behavior. The modified structure, put it again, maybe. The modified structure pretty much concentrates, I can show it here. It would still lead to some failure, but instead of having critical regions around the doors and windows and passenger area, it would be more concentrated in the angle area, which is places more suitable to collapse and to fail safely and without injuring passengers. So we decided to go a step further and also try to compare these models in terms of the European regulation. There are a bunch of design requirements. So we only compare this stage, these requirements in terms of survival space and acceleration levels. So maybe starting with the survival space. The regulation states a criteria that in that area, that it's the beginning of the passenger survival space, counting 5 meters, the reduction in length after the crash shall not exceed 50 millimeters, which is quite a difficult criteria. Here we have also comparative videos of that region between the original and modified structures. You can already see the difference. And when we plot the reduction in length of that section, we can see that, of course, the original structure failed the criteria. It surpassed the 50 millimeter mark, while the modified structure only reduced around 4 millimeters. When we compare a second criteria, which is the reduction in length in the final 5 meter of the vehicle, we also here have some videos. This was the hardest criteria, so to say, because even though the modified structure was able to be below the limit of the regulation, it was still close. So 90 millimeters. It was below, but with not a big safety margin. And finally, which is an interesting result, we analyzed the deceleration limits, which, as I showed before, it states that doing a moving average from 30 milliseconds, the acceleration levels in the structure should not surpass 10 G. Here's an interesting result because both structures would fail this criteria. And even the modified structure that performed very well in terms of survival space yielded even a higher acceleration level. After all the videos we saw, we can assure that we were able to modify the structure, but it's a bit rigid. It's important to have a balance between, okay, it should not be formed brutally, but also it should be formed enough to not absorb, but to dissipate energy and not transmit these higher levels to eventual passengers. So basically that's among the conclusions of our work. We were able to perform this kind of crashworthiness analysis under a head-on collision scenario. We identified critical failure regions and also studied a modified structure in terms of those regions. We found exactly that. The modified structure was able to improve the survival space criteria. However, it yielded higher acceleration levels because it is now more rigid. Overall, our research helped confirm that these kind of simulations are very important for the railway vehicle, also because of the higher cost of performing crash tests, and the regulations basically point us towards that direction. In terms of future work, we still have a lot to do. We need to still improve our model because there are a bunch of parameters we didn't analyze. And also maybe with the way we're doing it is not the best way to analyze it. So we still need to improve that. Also, we did this analysis for a simplified case. We still need to do it for the actual collision scenarios that are in the regulation. And this is very important. We are trying to explore simplification techniques because this model is huge. It takes time to simulate, and we are looking at strategies such as super element techniques and multi-domain techniques to try and shorten that time without compromising accuracy to give the answer to our industrial partners, which is, of course, very important. And also, if I may add, of course, validation of our model. We are in next year, we will be starting the testing campaign for static, not crash analysis. But it will be very important for us to validate our model through also those static scenarios. And that's it. Thank you very much for your attention.